So last week we talked about crystal structure, and we talked about how important the structure is to a material's properties. And I used initially the example of carbon, right? That carbon as graphite and diamond have very different structures, and they have very, very different properties. So I'd like today, now that we've talked about the crystal structure, to go over a little bit of what carbon looks like as diamond in terms of crystal structure and what carbon looks like in terms of as a graphite. Oh, we've already talked about that, but there was a question from your survey. Somebody wanted to know how you can convert graphite to diamond. So graphite, we talked about last time, has hexagonal layered structure. So it looks something like this. And it has each carbon bonded to 3 other carbons. And therefore, it has a delocalized electron that can move around. Okay. So if you apply heat and pressure, you can actually change the structure so that the carbon becomes bonded to 4 other carbons. So it's so it becomes a 3-dimensional bond, and that it no longer has a delocalized electron. It is much stronger because it's bonded to 4 other carbons and has a 3-dimensional structure, so it no longer has these layer properties where the layers can come off easily. Okay? But usually when this happens, when you do it industrially, the diamond that you form still has a hexagonal structure. It doesn't actually become a cubic structure like the diamond that you will find in nature. And so it is called hexagonal diamond. So yes, you could take graphite, you could apply a lot of heat and pressure to it, but you're still going to end up with and you will get diamond, something that looks and is called a diamond, but the actual crystal structure will be a little bit different than a diamond that you can find in nature, which has a cubic structure. So how can you grow a diamond or make a diamond in industry that actually has a cubic structure? So you usually start with cubic diamond, a very small one, and you use it as a seed. And then you add carbon to that seed at high temperature and pressure. And so because you're starting with something that's cubic, the other carbon that's attached to this seed will also be in the same structure. Okay, so I don't know if you've, in elementary school or in junior high, have ever grown a sugar crystal from a supersaturated solution. Have you ever done that, right? Like you add sugar to water and you boil it until you cannot add any more sugar, and then you let it cool. But when you let it cool, you put one sugar crystal, or you put a little string in the middle of that liquid, and then you'll see a growth of a sugar crystal. The slower you let it cool, the bigger the individual crystals will be. The faster you let it cool, you end up getting lots of tiny little crystals, right? So it's a similar process and concept. So if you allow, you have a seed with the structure you want, and you allow this carbon to slowly attach, then you could grow a fairly large diamond in the cubic crystal structure. Okay, and so you start with a cubic diamond seed, and you can add carbon in the form of graphite, but also you can add it as a chemical vapor, so in a gas form. So you can introduce carbon in the form of some sort of gas, and that carbon then will attach to the diamond seed and grow this larger diamond. So if you add it as a vapor, that process is called chemical vapor deposition, or CVD. So chemical vapor deposition is a fairly common process used to grow lots of different kinds of thin films or crystals or other things that you might need. Any questions about forming diamond? The temperatures and pressures are very, very high, so it's not something you could do in your house. And then another question from the survey has to do with carbon nanotubes. So some of you wanted to know more about what carbon nanotubes were. And so carbon nanotube is another form of carbon that's different than graphite or diamond. You can think of, there are several different types of carbon nanotubes, but the easiest way to think of them is if you took graphite, you took a layer of graphite, right, and you rolled it up into a tube. So we know that graphite forms in that hexagonal layer structure. It's called graphene, that structure. And if you took graphene and you rolled it up into a tube, then it becomes carbon nanotubes. So it's kind of like a tube of rolled up graphene. And then also, the way it's made is actually not too difficult. You need a catalyst, a source of carbon, and the temperature is usually about somewhere between, depending on the catalyst you use, somewhere between 400 to 800 degrees Celsius. So it's a much lower temperature than if you were trying to make diamond. Okay, any questions about making diamonds or carbon nanotubes? So because, oh yes?
How to roll it and then grind?
How do you actually roll it? So it depends on the catalyst that you're using. It will cause it to roll up into these tubes. And it actually, like compared to other things that you can make, carbon nanotubes actually are not that difficult to make. So yeah, you have to look up the different catalysts that are available, and then there's a different, it's essentially like a chemistry process. So yeah, so it depends on the catalyst that you're using. But if you're actually thinking about making them in a lab, there are lots of scientific papers that have detailed directions, instructions of when you need to add the catalyst, under what conditions to cause them to roll up. All right, so last week we started talking about points, directions, and planes in a crystal. And so today I want to go over some more foundational concepts behind points, directions, and planes in a crystal structure. So first of all, we talk about the distance between atoms, right? Like when we draw the expanded sphere model, so if this were the 1, 0, 0 plane in an FCC, and I were to draw the full sphere model, it would look something like this. They're touching. Yeah, all the atoms are touching. So how do we, and then here's the distance is 4r. So why would atoms have a certain distance apart? I mean, obviously it has to do with how many electrons they have, but it also has to do with the bonding that they form. And so I want to talk a little bit about energy versus distance in bonds. So E is energy, R is the distance between the atoms. And it looks something like this. The reason why energy is lower as the two, so you can imagine that you have one atom here and another atom somewhere out here, let's say here. The reason why the energy would decrease as they get closer together, any idea why the energy might decrease as they come closer to each other? Right. Because they can now start to share or transfer electrons, which would make them more stable, right? More stable means a lower overall energy state. So that's what this graph is showing you. As they come closer together, they can now interact with their electrons either by sharing or transferring. And so as they get closer together, the energy gets lower. Lower energy state, more stable. So here is sort of the ideal bond length, because that's the lowest energy. Any ideas why, if you were to push them closer together, why the energy shoots up like that? Right. The two atoms are too close together, the electrons are too close, the protons are also too close, right? So there's a repulsion. The Coulombic force, like charges, they repel each other, and therefore it's pushing the two atoms apart. And so there's an ideal distance for the two atoms to exist, where they have the lowest possible energy state. You push them too much closer together, they repel. You move them too far apart, their electrons are not able to interact effectively or efficiently. Okay? But this state is at the minimum energy. No other energy added to the system. We know that that cannot exist in real life. Anything that we use is usually, even if it's used at low temperature, it's not at absolute zero, it's not 0 Kelvin, right? So in anything that we're using, there's some amount of energy that's being added to the system. And so if we look at, let's say, E at room temp, RT is room temperature. So let's assume that this represents the system of the two atoms when it's at room temperature. We'll see that the atoms are actually vibrating between two different distances. The two atoms are closer, further, closer, further. They exist between those two distances. So they no longer have one distance apart. They're vibrating between two different distances based on the energy that's being provided. So instead of thinking as the two atoms being in a fixed distance apart, there's some movement to that distance and things can move around, okay? And so if you were to draw the average distance, you would follow, because the interaction is not as strongly dependent on distance, it's more of like a 1 over r squared, versus the repulsion is more like 1 over r to the 4th power. So this graph leans out this way. Okay, this is not as strongly dependent on distance. So the average r looks something like this. It occupies those two states, but the average is not a straight up and down line. It goes out towards increasing r. And this tells us that as temperature increases, the distance between atoms also increases. The r average increases, right? And this is what we experience in real life as things are heat up. As temperature increases, things expand, right? Materials expand, get bigger. Okay. But I want to show you something that is an exception to that rule. And the exception is because of the crystal structure. So if you study material science, you're going to study a lot about iron. Because iron is a main component of steel, and steel is used in so many different things. Of course, you'll study many other materials as well, but iron is kind of something that you'll be very familiar with if you're a material scientist. Okay, so in iron, at room temperature, iron is BCC, body center cubic, at room temperature. Okay, at temperature greater than 900 degrees Celsius, iron becomes FCC. I'm not going to go into the details of why that is. We will talk about the different phases of iron later in this course. But just know that it's more thermodynamically stable for iron to be in the FCC state when it's at a high temperature versus a BCC. So iron has this phase change at temperatures above 900. Okay. So if you were to calculate the size difference between BCC and FCC for iron, what would their size difference be? How would you do that? So calculate the unit cell size difference between BCC and FCC. All right, so how would you do that? So if we wanted to find the volume of BCC compared to the volume of FCC for iron, so it's the same element. R is the same, it doesn't change. Let's assume we're doing this at some set temperature. Obviously, it's a little bit different, but Let's assume that the R is the same for now. How would you solve this? How do you calculate volume for a unit cell? Yeah, you would need to know the radius of the atoms in the unit cell. But even if you didn't know the radius, you know that is the edge length cubed, right? Because it's cubic. We're talking about FCC and BCC, they're cubic. So this is equal to A BCC cubed divided by A FCC cubed. You know how to find the relationship between A and R, right? We've done that in the last class. Hopefully, do you already have the session with your TA? So hopefully he did some of that examples as well for you in class, in the recitation period. And so you know that A, or you could figure out that A of BCC is 4 divided by the square root of 3R, and A of FCC is 4 divided by the square root of 2R. You plug these two in, the R's cancel out, and you get 0.54. So this means that the BCC unit cell is much, much smaller than the FCC unit cell, right? It's almost half. But in actuality, the difference is closer to, the size difference is closer to 10% between the two structures because of the temperature difference. And then I wanted to talk a little bit more about the FCC. So the FCC, it's what is called a close packed. It has an atomic packing factor of 0.74. So the FCC is the closest packed structure that you can have. So you can't fit in any other, you have the 7 different Bravais lattices, the different kinds of crystal structures. It doesn't matter which ones you look at, you will not find another one that can fit more than 74% of its volume with atoms. So for a crystalline structure, 0.74 is the most densely packed structure that you can have. Okay, everything else will have a lower atomic packing factor. Another structure is the hexagonal close packed, which also has an APF of 0.74. And we didn't talk about hexagonal structures at all in this class, but you can look up pictures of it online or in your textbook. And I will try to draw. It looks something like this. And you have an atom on each of the corners. Okay, and then you have an atom in the center of each of the face. So this is the center. And then in the middle of this unit cell, you have 3 more atoms that are completely encased within. Something like that. Okay, so that's a hexagonal close packed HCP. And this also has an atomic packing factor of 0.74. So the reason why these two are important is because if you know that they're either the FCC or HCP, that it's the most densely packed structure that you can have for any element and for any structure. So that's its significance in terms of understanding material properties based on crystal structure. So FCC and HCP are a little bit special. So now I want to talk a little bit about how, as material scientists, you can figure out what structure materials are. So how do you know if the iron you have in front of you is a FCC or BCC, or if the carbon in front of you is a hexagonal diamond or a cubic diamond? Right? How do you know that? So with that, we use light to investigate the structure of materials. So use light. So hopefully in your physics classes, you've learned about light being both a photon, which is a particle, and a wave, right? Light, it has a dual property. We could represent light as a wave or a particle. And the relationship between light as its energy, as a photon, and its wavelength as a wave is based on this equation. So E is the energy of the photon. Lambda is the wavelength. H is Planck's constant, which is 6.63 times 10 to the negative 34 joules second. And C is the speed of light, which is equals to 3 times 10 to the 8th meters per second. Okay. So anyone know the wavelength range for visible light? Roughly, yeah. So it's in between 400 and 700 nanometers, and it's between 3 eV and 1.75 eV. And we know that lambda, or the wavelength, the energy is inversely related, right? E is proportional to 1 over lambda. And so that at long wavelength, you have low energy light. At short wavelength, you have high energy light. So long wavelength or low energy light is what color? Red. And high energy or low wavelength light is purple or violet, something like that, right? Okay. And what if you have things that are longer wavelength, lower energy than 1.75 eV or 700 nanometers? What is that called? Infrared, right? So lower than red. So IR, infrared, just means lower than red, and so that's a longer wavelength or lower energy than 1.75 eV or longer wavelength than 700 nanometers. What is on this side? If it's higher than violet, ultraviolet, okay? That's what the term means. Ultraviolet, you have shorter than 400 nanometers or a larger energy than 3 eV. X-rays, it's another form of light, a very high energy light. So X-rays, the energy is between, it's 100 eV and 100,000. So light between 100 eV to 100,000 eV is considered an X-ray. So this is the wavelength that is between 0.01 nanometer to 10 nanometer. So we actually use X-rays to investigate the structure of crystal structures or of materials. And the reason why is because the wavelength is near the same size as the size of an atom. So the radius of iron, it's around 0.1 to 0.2 nanometers. And the crystal lattice, the size of a unit cell, is roughly 0.3 nanometers. So when we use light, visible light, to look at iron, we can't see the crystal structure because we're talking about using something that's like 700 nanometers to look at something that's 0.3 nanometers, right? The resolution's not good enough. You shine light that is that long wavelength over something that is that small is like, it's like us thinking that this table is really smooth. We know if we took a microscope and looked at this tabletop, you would see lots of divots, right? It's a very rocky space. But our fingers are so big that we don't feel the individual holes and dents and things. So when we move our finger across the table, it feels smooth to us because our fingers are big compared to the small holes in the table. So same thing with the light. If we use the visible light to look at iron, it would just look smooth to us because it doesn't have enough resolution to be able to tell all the different small spaces in between. So that's why we have to use X-rays. X-rays have a similar wavelength to the size of the atom, and therefore it could see the structure. So in order to understand how we can use X-rays, I'll talk a little bit, very, very briefly, about constructive and destructive interference with waves. I think you all know this already, so I won't spend a lot of time. So if you have two waves, something like that, they match up, right? The peaks and the valleys match up and they interfere with each other. Then you get something that has increased intensity, right? So constructive interference, this is constructive. But if the two are not perfectly matched up, something like that, then you could get destructive interference. So you actually get something that's more muted like that. Less intensity. Okay, I think you've all learned about this before in physics, yeah? Okay. So this is destructive interference. So we use this principle to investigate the structure of lattices. So if we have a crystal lattice, so we have our atoms. Okay. Let's see how I can draw this. One beam of light, another beam of light. Okay. So we're shining a coherent light beam at our material. So that means all the wavelengths are the same. It's not a broad spectrum light. We're using X-rays of one particular wavelength. So the wavelength of this beam and the wavelength of this beam is exactly the same. Okay, we take that X-ray, we shine it at our material. And the light beams that hit the atom will be reflected. And will be reflected at the same angle that it hit the atom, right? So it will something like that. So we'll have some incidence angle. So theta is our incident angle. So the angle with which it hits, which is the same as this angle, right? So the incident ray angle and the reflected angle is the same. So this light beam comes this way, hits this atom, gets reflected. This one goes a little bit further, has to travel a longer distance. If this is our light source, depending on where the X-ray hits the atom, which plane, it travels a different distance, right? This one travels this distance extra, and then also this distance. And we have something called Bragg's law that describes this for us. N is the order of reflection. Lambda is the wavelength of our light. D is the distance between the planes. And theta is the angle here, the incident angle of the light. So if these two wavelengths match up, it will have constructive interference. right? If they happen to perfectly not match up, they will have destructive interference. Somewhere in between, they will have a lower intensity. So whether they match up really depends on what the angle is and what the distance is, whether the two light beams that come out of that material will match up or not. Okay, so if you were to look at a plot of X-ray diffraction, it'll look something like this. You have intensity versus 2 theta. And this is just a made-up material, something like that. Okay, you'll get this graph with peaks. The peaks are intensity, how intense that light beam is. So this is capturing what comes out after you shine an X-ray at a material. The 2 theta means that you are rotating the beam around some different angles. So you're shining the X-ray, but you're not just shining it at the material in one direction. You're alternating, or you're varying that angle. You're looking at the material through all different degrees. Okay, 2 theta. And by varying the theta and figuring out the intensity, you will know the distance between the planes. So you can now tell how far apart the atoms are from each other, and also where the atoms are located, how far apart they are this way, because you know if another beam might be like this, right? And this beam would not be any different because they've traveled the same distance. And maybe another beam comes down all the way to the third one. So that would be a third order reflection. And it has traveled a much further distance than that first beam. Okay, so you're looking at lots of beams shining on your material. You're varying the angle. You're looking at what comes out. And this actually will tell you, by doing the calculations and studying all the different peaks, that, oh, this is a 110 plane, this is a 200 plane, this is a 111, for example. So by using X-rays to investigate the material, you can find out the different planes that exist. And so that will tell you if it's a cubic, hexagonal, orthorhombic. It will tell you the distance between the planes. Okay, so you can actually, all the stuff that we've been drawing can be figured out by using X-ray diffraction. All right, so we'll go over a little bit more about crystal structure on Friday tomorrow, and then get into defects.